note that A vector is parallel to B vector if and only if A vector is some scalar multiple times B vector. Um, so if this is A vector right here, then basically the concept of this is pretty easy. If this is some constant times B vector, where in this case A vector, that constant, if this is B vector, you know, it looks like, you know, in this case A vector is 1/2 times B vector, so they're in the same direction there and stuff. Now it is true this is you know, exactly the same, but we could have, you know, B vector be here, and then A vector could have a different representation, right? And being somewhere like here, and those are parallel as well, because we can move that representation, right? So we could also talk about position representations of that as well. We could put them both on the origin. So anyway, so if a representation is a scalar multiple of the other, then they're going to be parallel vectors as well. Let's just note one thing here is some of the things that we did always, sometimes, or never, but I had zero vector always is going to equal 0 times A vector, where the zero vector and A vector have the same dimension, right? So this is always true if they have this zero vector and A vector have the same dimension. So anyway, because of that, because we can write zero vector as a constant multiple times A vector, then we can say that the zero vector is parallel to any vector, A vector. So that's kind of a nice result there. And then I believe I said this wrong to Jordan yesterday, but now we talked about perpendicular vectors, also called orthogonal vectors. So A vector is perpendicular to B vector. Also said A vector is orthogonal to B vector. These are orthogonal vectors, is another way we can say that, if and only if their dot product is 0. So if their dot product is 0, then they're perpendicular to each other, which means that theta in between is going to be equal to pi over 2, or 90 degrees. So that is, it looks like a dot. Sometimes that's approximately equal. Let me erase that because it's exactly equal to 90 degrees, or pi over 2 radians. But the question is the zero vector orthogonal to any vector? Well, if you take two vectors, so zero vector dot A vector, does that equal 0? Well, if and only if they're the same dimensions, right? This is true if the zero vector and the A vector are the same dimensions. But if they are the same dimensions, basically what this says then is the zero vector is going to be orthogonal or perpendicular to any vector in the same space, because it always has a dot product of 0, right, in the same space if they have the same size. So I did mention that. I said that wrong yesterday. That is wrong in your notes, because your notes say zero vector is not perpendicular to any vector, but that's not true. It's actually perpendicular to any vector in the same dimension. Okay, so let's move along from that. Let's do a couple examples. Then I screwed up an example at the end of the day yesterday also, so I'm just gonna make sure I don't do that this time. So let's look at an example. If I have, let's just let A vector equal, I'm going to change this up. I'm going to say 3i hat plus 4j hat plus 4j hat. And B vector, I'm going to say this is 5i hat plus c hat. So in other words, I don't know what the coefficient here is, and then I've got two different problems. So the first thing, I need to find a c such that you know, they're parallel. So if A is parallel to A vector is parallel to B vector, I want to find that C. Well, what do we know about scalars? So A is parallel to B if and only if there exists some constant, an element of the real numbers, such that what? Such that A vector equals that constant times B vector. Okay, well, I'm going to write this in vector notation. So 3, 4, vector 3, 4, and vector 5c. And so really what I can do here is say, well, A vector is 3, 4, and that has some constant times B vector, right? So this is gonna equal K times 5c, which equals the vector 5k and ck. And then what do I have to have? That equals 3, 4. So then I have two things here. I've got that 5k equals 3. So if 5k equals 3, then that implies that k equals 3/5, right? And then I also have that ck equals 4, but we know what k is, so I can drop that in right here. So 3c over 5 equals 4, and then that implies that 3c equals 20, so c equals 20/3. Okay, so that's what we're looking for in this case to be parallel. So anyway, that should help out. So if this, I guess coming back, and if I put in, we could check and verify that we're right. So if I have 20/3 here, oops, if I have 20/3 here, then basically, how do I check that they're parallel? Well, does 3/4 equal some constant times B, right? So so does 3/4 equal, what did we say K was? 3/5 times 5, the vector 5c, but if this is 20/3, then I'm just going to multiply this out. So 3/5 times 5 does equal 3, so I get a check on that one. And then 3/5 times 20/3, the 3's cancel, 20 divided by 5 is 4, so I get a check on that. So we can check that out, and we're good to go there. So I just want to make sure that I remember this. So 3, 4, 5c. Now I want to look at what would the C be that makes that parallel, perpendicular, orthogonal, where we did parallel. All right, so let me go back and solve that one. So part 2 now is we need to find the C such that A is orthogonal or perpendicular. A vector is perpendicular to B vector, and of course, A vector, let me just rewrite it so we don't forget it. We said 3, 4, 5. So it's 3i plus 4j. B vector is 5i plus cj. So rewriting that 3, 4, and 5c. What do we know about orthogonal vectors? This is true if and only if, so I'll just do that up here. If and only if A vector dot B vector equals 0, right? So we're gonna say A vector dot B vector down here. This is 3, 4 dot 5c, and then of course this is a scalar, right? So we just put them on top of each other, multiply and add. So we get 15 plus 4c, and what do we know about that? That has to equal 0 if they're going to be orthogonal to each other. So that implies that 4c equals negative 15, and that implies that c equals negative 15 fourths. Okay, so once again we can check that. I'm just going to go back and put negative 15 fourths here in for c, and if I take that dot product, negative 15 fourths, then I've got 15 just like I did before, but instead of 4c, it's going to be 4 times negative 15 fourths. It's going to be 15 plus negative 15, which does equal 0. So I not only found the c, but I verified that that c worked. Okay, so let me erase this and move along, and let's talk about projections. Okay, so we've got scalar projections and we've got vector projections. Okay, and there is a distinct difference here. So let's define what a scalar projection is first. And so I've got this in two different places in the notes. So like page 12 at the top is the second part. I also did it, must have been on page 11 and a half, or 11 and 2/3 down toward the bottom. I started talking about it, but really if you go to page 12, I kind of redid it, and it's a little bit cleaner from the start. So what is a scalar projection? Let's define what a scalar projection is. Okay, so remember a scalar is a number. So we've let A vector and B vector be non-zero vectors. So these are non-zero vectors. They're vectors by their notation, so I could have just said not equal to 0. Not equal to 0 vector. So instead of writing this part right here, I could have just said they don't equal 0 vector in the same of the same dimension. But anyway, then the scalar projection. Remember scalar, number, constant. The constant or number projection of B vector onto A vector. And you got to kind of pay attention which one's first. So B vector onto A vector. So scalar projection of B vector onto A vector is given by the norm of B vector times the angle in between, cosine of the angle in between. Norm of B vector times cosine theta. Now, notice the norm of B vector is a number, right? And cosine theta is a number. So this ends up being a constant or a number. So that's important to know. But we also have a proven, but let me draw this. So if I've got B vector here and I've got A vector here, and then I've got the angle theta in between, the number projection scalar of B vector onto A vector is going to be given by B vector cosine theta. So let's have a follow-up theorem on this. So that's defined to be that way, but we know from a theorem that cosine theta equals A vector dot B vector over the norm of A vector times the norm of B vector. So that was a theorem that we had a couple of days ago. So what I can do is I can plug this in right here for cosine theta. And so then we can rewrite the scalar projection as the norm of B vector times, instead of cosine theta, times A vector dot B vector over the norm of A vector, norm of B vector, and of course what happens to the norm of B vector? That's a number, but that cancels.